Imagine throwing a needle at a spinning record. The needle lands perfectly in the groove, travels flawlessly for one full turn, and then slips into the darkness. The odds? Almost zero. Yet 3I Atlas did exactly that. It entered our solar system as if passing through a cosmic needle's eye, dodged deadly gravitational traps, and carved out a flawless orbital path. So flawless, it made us wonder if it could really be just a coincidence. In the midst of chaos, such perfect harmony. Do you think this is merely chance, or was 3I Atlas's trajectory planned all along? Hold on tight. Today, the truths about 3I Atlas will be revealed. If you're ready, let's begin. On the night of July 1, 2025, while the Atlas telescopes in Chile were conducting a routine asteroid scan, they made a discovery that would change the history of humanity. The two Atlas telescopes that made this discovery had not made an ordinary detection. This discovery would open the door to irreversible questions. That night marked the beginning of our story. Sit back and prepare your coffee. The detected object, 11P3Z, at first glance seemed like an ordinary asteroid, but with its incredible speed of 57,000 kilometers per second, it shattered all expectations. This speed was high enough to circle the Earth in less than 12 minutes, which clearly showed that the object was moving in a hyperbolic orbit, meaning that it did not belong to our solar system. The Minor Planet Center in Cambridge confirmed this extraordinary situation within 24 hours. The object's eccentricity was close to 6.1. This number indicated that it was not gravitationally bound, and that we were facing a visitor from interstellar space who would return there. Why had this mysterious visitor from the vast depths of the galaxies come to our galaxy now? What did it want? Was it just an asteroid? This object, named 3I Atlas, Interstellar Atlas, became the third confirmed interstellar object detected by humanity. Like the first two, Oumuamua, 2017, and 2I Borisov, 2019, this new guest excited the scientific community but carried its own unique mysteries. So, if you were in this situation, how would you feel upon encountering such a discovery? Fear or curiosity? One of the most striking errors in the initial observations was in estimating its size. Early reports suggested that the object could be up to 20 kilometers in diameter, large enough to contain entire cities. While the media covered it with headlines like "Giant Mothership," this exaggerated reaction was similar to tourists overreacting in a foreign country. These misleading reactions were like missing a dartboard from 1 meter away compared to the real result, which turned out to be much more modest. When the sharp eyes of the Hubble Space Telescope managed to distinguish the nucleus within the surrounding cloud of gas and dust, the picture changed. The real nucleus was only a few kilometers in diameter, perhaps even less than 1 kilometer. This revision was due to incorrect assumptions on the object's surface reflectivity and miscalculations of the coma's contribution to its brightness. The global coordination that followed the discovery showcased the power of modern astronomy. Within 24 hours, observatories on 6 continents turned their telescopes to 3I Atlas. The scientific community began moving in a coordinated way, as if each scientist and each observatory were one body. In a world where solidarity in science was this strong, nothing could bring it down. Amateur astronomers worked shoulder to shoulder with professional teams, while the Virtual Telescope project hosted live observation sessions. NASA and the European Space Agency made highly measured statements. Yes, this was indeed an interstellar object. No, it posed no threat to Earth. And yes, it was an unprecedented opportunity to study material from another star system. The frequency of such discoveries is increasing. What other surprises might we encounter in the future? The discovery of 3I Atlas showed how much progress we have made in our astronomical infrastructure since Oumuamua in 2017. The Atlas system, 4 telescopes in total, 2 in Hawaii, 1 in Chile, and 1 in South Africa, was actually designed to detect potentially hazardous asteroids. The fact that this network was also effective in detecting interstellar visitors was a happy coincidence of geography and timing. Archival research revealed that the object had actually been detected on June 14, or probably even earlier. These precovery observations significantly improved orbit calculations and made it possible to predict future positions more accurately. Unlike Oumuamua, 3I Atlas showed noticeable cometary activity from the moment it was discovered. Hubble images revealed a glowing coma and a faint tail, exactly what one would expect from an interstellar icy body in the solar wind. However, some things looked strange. Early observations showed that most of the brightness was concentrated in front of the object's direction of motion, while the conventional anti-solar tail stubbornly remained weak. It was as if the laws of physics were slowly losing their effect, as if a loophole in the laws was being used, yet these laws were the laws of the universe. They could not be bent or twisted like this. Some researchers began whispering about forward scattering effects and unusual dust dynamics. Being aware of such anomalies is critical in scientific discoveries. What deviations from normal do you notice in your daily life? Media attention was immediate and intense. CNN broadcast segments comparing 3I Atlas with Oumuamua. The Guardian published explanations about interstellar objects and what their compositions could tell us about other planetary systems. However, perhaps even more interesting than the discovery itself was what we learned about our own capabilities. Specifically, in the case of the Atlas system, it turned out that it functions as an early warning system against threats coming from space, while also serving as humanity's first line of defense in detecting objects from other star systems. Predictions that the Vera Rubin Observatory will discover dozens of such objects in the next decade are both exciting and worrying. Among these mysterious objects, those that are treasures for the scientific community must definitely not be missed. These mysterious treasures could change the fate of humanity forever. Through these treasures, perhaps we could even find ways to reach speeds close to the speed of light. Each one may have unique characteristics and challenge the limits of our understanding in different ways. The discovery of 3I Atlas answered one question. Indeed, we were observing humanity's third confirmed interstellar visitor. However, it raised dozens of new questions. Where exactly had this object come from? What was its internal composition? How large was its nucleus beneath the growing coma? And perhaps most fascinating of all, why did its orbit seem to follow such a precise path within our planetary system? Amateur astronomers and professional researchers prepared for the months ahead, knowing that 3I Atlas would brighten as it approached the Sun. This increase in brightness could reveal secrets about the formation and evolution of planetary systems light years away. The discovery phase had ended. Now a much more challenging task began: understanding what we had found. The night sky had presented another mystery, wrapped in the deceptive simplicity of a moving point of light. While telescopes around the world continued their patient watches, one thing was certain: 3-Eye Atlas would teach us something new about the universe we thought we understood. Which answers in this cosmic mystery are you curious about? Share them so we can continue this journey of discovery together. Nothing in the universe moves randomly. Every orbit is a precise curve drawn according to the mathematical rules of gravity. Yet the path followed by 3-Eye Atlas seems as if it were designed by a cosmic choreographer. The universe's harmonious dance becomes even more defined and beautiful with each planet's orbit. Planetary paths create the movements of the universe's dance. This geometric precision both fascinates and unsettles scientists. Entering the solar system at an inclination of 175 degrees, 3-Eye Atlas moves on a retrograde orbit. That is, in the exact opposite direction of our planet's motion. But the most striking aspect is that this motion deviates only 5 degrees from the ecliptic plane. This deviation is so small that it is less than the width of an average human hair. Such a tiny misalignment provides evidence that massive planets do not wander randomly. One could even call it a miracle on matter itself. In three-dimensional space, an object can literally approach from any direction. The ecliptic plane represents a paper-thin slice among these infinite possibilities. Imagine an orange. The ecliptic plane is like the thinnest slice cutting through it. 3-Eye Atlas hitting this slice almost perfectly represents one possibility out of millions. Faced with such precise alignment, what would you feel? Coincidence or design? However, this miracle might be influenced by observational biases. Ground-based sky surveys focus on the ecliptic for practical reasons, because most asteroids and comets are there, and observation conditions are optimal. For every object discovered at high inclinations, we may find only one in other directions, because we are not looking as carefully. 3-Eye Atlas's sequence of planetary encounters looks almost like a carefully planned tourist route. October 3, 2025. Encounter with Mars at 1.9 astronomical units, about 19 million miles. November 3, 2025. Passage by Venus at 0.65 astronomical units. December 19, 2025. Approach to Earth at 1.8 astronomical units. March 16, 2026. Final encounter with Jupiter at 0.36 astronomical units. At first glance, this chronological sequence seems like an intentional inner solar system tour, as if following an ordinary guide. Yet orbital mechanics tell a different story. These close encounters are actually too distant for any meaningful gravitational interaction. 3-Eye Atlas does not gain gravity assists from the planets, does not change its orbit, and does not steal energy. By spacecraft standards, these distances are large. The object almost entirely ignores the gravitational wells of the planets. Any object on a retrograde hyperbolic trajectory that grazes the ecliptic plane will necessarily encounter multiple planets at various distances. The specific order and timing depend on precise orbital geometry, but multiple planetary encounters are almost a guaranteed outcome. So do you think this coincidence is really a coincidence, or is there a deeper order at work? During its perihelion passage on October 29, 2025, 3-Eye Atlas will be positioned behind the Sun and will become almost completely invisible when viewed from Earth. This solar conjunction makes detailed observations nearly impossible at the time when the object should be most active. Skeptics might argue that this is a convenient timing to avoid close scrutiny. However, astronomers note that for any object with a perihelion distance of 1 to 2 astronomical units, a solar conjunction is a geometric necessity. 3I Atlas seems to have chosen to hide its most active moments from the scientific community. Let's see how much it can really conceal from modern science. The Hubble Space Telescope has produced stunning orbital visualizations showing 3I Atlas's path. These diagrams reveal the ballistic precision of celestial mechanics, how gravity shapes motion over millions of miles with mathematical perfection. At the same time, they emphasize the apparent intentionality of the path, a trajectory designed to provide a glimpse to multiple worlds, yet never close enough to be captured or deflected by any of them. Observational uncertainties add another dimension to the puzzle. Although the overall shape of the orbit is well determined, precise distances and timings still carry margins of error. The perihelion distance, indicated as 1.36 to 1.4 astronomical units, reflects the uncertainties in the current orbital solution. This uncertainty is both frustrating and significant. It prevents us from making definitive statements about the object's path, while reminding us that our observational capabilities may reflect the limits of our instruments more than the designs of the true cosmic choreographer. Does this uncertainty disturb you, or does it make the mystery even more compelling? Each new positional measurement helps narrow the error ellipses around future positions. When 3I Atlas reaches perihelion, we will have a much more precise understanding of exactly where it is going and when it will arrive. Additional astrometric observations continue to refine these orbital elements. The coordination of professional observatories and the contributions of amateur astronomers play a critical role in determining the object's true orbital parameters. Scientists are attempting to predict 3I Atlas's orbit in advance and have largely succeeded, but any external factor could cause 3I Atlas to deviate from its path. This concerns scientists because 3I Atlas is the largest interstellar object we have ever seen. The orbit raises fundamental questions about how often random walks in the universe produce paths that appear so organized. As an inevitable result of advanced detection capabilities, are we noticing unusual circumstances? Unusual cases attract our attention because they are unusual. Or does it reflect something more deliberate? As 3I Atlas continues its precisely choreographed dance through our solar system, these questions become more than academic curiosity. In a universe where natural processes can produce patterns that appear extraordinarily intentional, our understanding of what constitutes evidence of intelligence is challenged. The geometry is clear. The interpretation, however, remains fascinatingly ambiguous. Perhaps the greatest mystery of the universe lies in how design and chance can speak the same language. This cosmic ballet both terrifies and mesmerizes its observers. Was 3I Atlas's orbit truly chosen, or did we choose to notice it? This distinction may be far more important than we are willing to admit. Faced with this cosmic choreography, what emotions do you feel? Curiosity or concern? Share your thoughts. This mysterious visitor from the depths of dark space, at first glance, appeared like a typical comet. Yet the physical characteristics of 3I Atlas contain details that both astonish and concern scientists. Thanks to the sharp eyes of the Hubble Space Telescope, these features emerged, dancing on a fine line between natural explanations and unusual theories, like an acrobat walking on a thin 50-meter rope while performing risky maneuvers. Scientists have not yet fully understood these dangerous movements, but in the future, the situation may change. Over the months since the first discoveries by the Atlas telescope system, each new observation has provided fresh clues about the complex nature of 3I Atlas. The most striking feature of this interstellar comet was the prominent activity it exhibited as it approached the Sun. Like other comets, 3I Atlas developed a bright coma and a faint tail as the ice within sublimated under the influence of solar radiation. The most important finding revealed by Hubble observations was that the object clearly exhibited cometary activity. This indicated that, unlike the mysterious behavior of Oumuamua, 3I Atlas followed more familiar physical processes. However, familiar did not mean ordinary. The mystery remained unsolved. Yet, how long could the secret protect itself from the sharp intellect and keen eyes of modern science? High-resolution images from Hubble showed that 3I Atlas was surrounded by a gas and dust cloud, coma, approximately 100,000 kilometers wide. This coma was continuously shaped by the solar wind, leaving a characteristic tail behind the object. These images, the most significant discovery of the 2025 comet year, allowed scientists to calculate the object's true size. Initial estimates suggested that Atlas could be 10 to 20 kilometers in diameter, but Hubble's detailed analyses dramatically reduced these numbers. The actual nucleus likely had a radius smaller than 2.8 kilometers, and some models even indicated it could be below 1 kilometer. This size revision was not just a measurement error, it raised profound questions about the nature of the object, causing the alarms in scientists' and the scientific community's minds to ring intensely. Although the intensity of these alarms gradually decreased day by day, the clouds of questions had not disappeared. The dust production rates of 3I Atlas were considerably higher than expected for objects in the interstellar category. Calculations based on Hubble observations indicated that the object produced between 10 and 120 kilograms of dust per second. Although these numbers sound very large, for a nucleus only a few kilometers in diameter, they were actually at sustainable levels. However, the most interesting aspect was the optical effects created by this dust production. Unlike most comets, the brightness of 3I Atlas was concentrated on the side facing the Sun. This forward scattering effect deviated from conventional cometary behavior and led some researchers to think that the object might have unusual dust properties. Uncertainties regarding the size and distribution of the dust particles constituted a critical obstacle in understanding the true nature of 3I Atlas. Different particle sizes could create completely different scattering patterns, which could significantly affect the object's brightness distribution. Was this uncertainty a coincidence, or did it hide a deeper truth? It was a symbol of how complex nature is, perhaps even a miracle. The universe we live in is full of such miracles. Coincidence? No, impossible. If there is art, there must be an artist. Spectroscopic observations aimed at understanding the chemical composition of 3I Atlas presented unexpected challenges. the most advanced telescopes on Earth struggled to detect the expected types of gases in the object's atmosphere. Clear spectral signatures of typical cometary gases, such as water vapor, carbon monoxide, carbon dioxide, and cyanide, were not found. This situation drew the attention of scientists like Avi Loeb. Loeb began to raise the alien probe theory he had proposed for Oumuamua in the context of 3I Atlas as well. The insufficiency of the spectroscopic data suggested that the object could have a composition different from expected, or that gas production was occurring through unusual mechanisms. However, there were entirely natural explanations for these spectroscopic difficulties. 3I Atlas's distance from the Sun and relatively low activity level caused weak emission lines to be lost within the background noise. The experience with the interstellar comet 2I Borisov showed that patience was necessary. The most prominent chemical signatures of that object were only detectable as it approached perihelion. One of the most interesting details revealed in Hubble images of 3I Atlas was the object's perfectly asymmetric brightness distribution. The dust emission appeared slightly offset from the center of the nucleus, indicating the presence of localized gas outflows. In most comets, solar radiation heats the nucleus relatively evenly, which leads to symmetric activity patterns. However, the asymmetries observed in 3I Atlas suggested either that specific regions on the object's surface had different volatile concentrations, or that more exotic energy sources were present. These morphological details also provided clues about the object's rotation state. Most active comets show clear periodic changes in brightness and morphology as different surface regions rotate in and out of sunlight. The absence of distinct cyclical signatures in 3I Atlas pointed to either an extremely long rotation period, an almost spherical shape, or a viewing geometry that minimized the visibility of cyclical effects. This implied that the object might be rotating on its axis, from which we can draw the following conclusions. It could be a perfect sphere, or it could be an extremely slowly moving object. The thermal behavior of 3I Atlas added another piece to the puzzle. As the object approached the Sun, its increase in brightness followed typical cometary models, but there were deviations in fine details. These deviations suggested that the surface materials of the object might have thermal properties different from expected. Albedo, reflectivity calculations were filled with uncertainties. How much sunlight the object reflected and how much it absorbed directly affected size estimates. Low albedo values indicated that the object was larger, but darker, while high albedo values suggested smaller, but brighter surface materials. These thermal properties were not just a matter of academic curiosity. If 3I Atlas were indeed an artificial object, the thermal emission patterns would rank among the strongest evidence to reveal it. Natural objects exhibit predictable thermal behaviors under solar heating. Artificial objects, however, could show different signatures due to internal energy sources. Changes in 3I Atlas's activity as it approached the Sun were carefully monitored. Unlike most comets, the object began exhibiting activity earlier than expected. This suggested either the presence of near-surface ices or more efficient sublimation mechanisms at work than usual. This precursor increase in activity levels provided important clues about the internal structure of 3I Atlas. If the object had a loose rubble pile structure, solar radiation could easily penetrate the interior and allow gas to escape from a wide surface area. Alternatively, cracks or voids near the surface could grant early access to deeper ices. This activity pattern was critical for future observations. How 3I Atlas behaved during and after its perihelion passage could provide final clues about its true nature. Natural objects usually fragment or exhibit dramatic changes in activity levels under thermal stress. This thermal ordeal would be like a cruel torture for 3I Atlas. Maintaining its integrity during this process was crucial because if it lost its durability, it would break apart. The uncertainties and anomalies in 3I Atlas's physical characteristics were not only a matter of scientific curiosity, but also constituted a methodological test. Studying this interstellar object improves our ability to analyze similar objects we may encounter in the future and exposes our limitations. With the upcoming commissioning of the Vera Rubin Observatory, dozens of new interstellar comets are expected to be discovered each year. This increasing rate of discovery will limit the time available for detailed analysis of individual objects, while also providing opportunities for statistically meaningful comparisons. The physical characteristics of 3I Atlas serve as a reference point for future studies. Which features are truly unusual and which are merely reflections of the limits of our observational techniques? The answers to these questions will not only help us understand the nature of 3I Atlas, but also shape our comprehension of our place in the universe. Currently, 3I Atlas is becoming increasingly active as it approaches the Sun, revealing new secrets each day. The most important lesson this 2025 comet may teach us is perhaps to learn to live with uncertainty and embrace the questions that each new discovery brings. The most elegant explanations in the history of science are usually the simplest, and in astronomy, this generally points to the well-tested physics of ice, dust, and sunlight. Despite all of its unusual features, 3I Atlas displays the fundamental signature that immediately classifies it as a natural object. It is actively releasing gas, just as a comet should. So, is this enough evidence to label 3I Atlas as natural? The basic physics is quite simple and has been refined over decades of studying comets in our solar system. As 3I Atlas approaches the Sun, solar radiation heats its surface and causes the subsurface ices to sublimate directly from solid to gas. This escaping vapor also carries small dust particles mixed with the ice, forming the characteristic coma surrounding the nucleus, that cloudy envelope of gas and dust. Hubble telescope observations confirm that this process occurs exactly as theory predicts. The images show a well-developed coma with clear sunward dust emission and a weak anti-sun tail. The sunward emission appears where solar heating is strongest, triggering the most intense sublimation. The tail forms as radiation pressure from sunlight pushes the lighter dust particles away from the nucleus. We can think of it like entering a house that hasn't been swept for 3 years and using a broom to clean the dust. Sunlight acts like a cosmic vacuum, sweeping the particles away. The estimated dust production rates from these observations, 10 to 120 kilograms per second, depending on particle size assumptions, fall completely within the range observed in active comets of our own solar system. While this may seem like a lot of material, it represents an infinitesimally small fraction of the object's total mass. A nucleus, only 2 kilometers in radius, contains roughly 4 billion kilograms of material, meaning 3I Atlas could sustain its current activity levels for thousands of years without noticeable depletion. Surface brightness modeling using Hubble data constrains the nucleus size to less than 2.8 kilometers in radius, with some solutions suggesting an object smaller than 1 kilometer. This size range is perfectly reasonable for interstellar object debris. Planet formation processes inevitably produce large amounts of leftover material in this size range, and some of it is ejected from their primary systems through gravitational interactions with planets or stellar companions. The forward scattering brightness pattern, which has sparked speculation about artificial illumination, finds a much simpler explanation in dust physics. When small particles scatter sunlight, the efficiency strongly depends on the scattering angle, the angle between the incoming sunlight and the observer's direction. Forward scattering, when light approaches from behind the particles, can be dramatically more efficient than backscattering for certain particle size distributions. This effect explains why 3I Atlas appears brightest in the sunward direction without requiring any exotic energy source. The dust grains in its coma create a view that may appear unusual to observers unfamiliar with the subtleties of optical scattering, efficiently scattering sunlight when viewed from certain angles. We had never before seen an interstellar object producing such strong sunlight-driven geometric brightness patterns. It should be noted that interstellar comet 2I Borisov displayed similar characteristics. That object also exhibited variable brightness patterns depending on the geometry of sunlight, yet this never produced any exotic interpretations. Similar phenomena in 3I Atlas became noteworthy only because they were observed more prominently. Its orbital dynamics also follow natural patterns. The hyperbolic orbit, with an eccentricity of approximately 6.1, indicates an object moving at typical interstellar object speeds. The V-infinity of 58 kilometers per second matches exactly what we would expect from debris originating from the galactic thick disk and encountering the solar system's gravitational well. These speeds are neither exotic nor artificially engineered. They represent the natural outcome of stellar motions within our galaxy. Stars rotate around the galactic center at different velocities, depending on their distances and orbital properties. When material is ejected from a stellar system and later encounters another system, the relative velocities typically fall within the range observed for 3I Atlas. The visually striking near-ecliptic alignment becomes far less mysterious when viewed through the lens of observational selection effects and gravitational focusing processes. Ground-based sky surveys concentrate their efforts near the ecliptic for practical reasons. Many of our telescopes, like air in a bottle, observe only a single plane where our planets and many objects traversing space are located. The ecliptic plane is not arbitrary. It represents the gravitational midplane of our solar system, where the combined mass of the Sun and planets creates a kind of cosmic basin line capable of steering incoming objects toward this plane. The apparent targeting of the ecliptic may reflect natural gravitational dynamics rather than intentional navigation. Alien probe theories proposed by Avi Loeb and other researchers do not fully account for these gravitational focusing effects. Why an advanced civilization would choose to approach the solar system along such a convoluted path remains unclear, especially considering that this approach offers no obvious operational advantage. Even the sequence of planetary encounters, which superficially looks like a planned tour, results from similar orbital geometry. A retrograde orbit skimming the ecliptic naturally brings 3I Atlas past multiple planets at several astronomical units. However, the missed distances are far too large for meaningful gravitational interactions. These are not targeted flybys, but merely the inevitable result of passing a system along a hyperbolic path where most massive objects are concentrated near a single plane. The timing of the solar conjunction also finds a simple explanation. Any object with a perihelion distance of roughly 1 to 2 astronomical units will inevitably pass through conjunction when viewed from Earth. This is not a feature designed to avoid observation. It is simply the predictable result of orbital mechanics. The timing is not particularly exotic either. Objects with similar perihelion distances include numerous asteroids and comets that regularly experience conjunction during their perihelion passages. Over time, if we had studied all these objects, we would have found that conjunction during perihelion is the rule, not the exception. Yet our brains resist this statistical argument because it conflicts with our deeply rooted intuitions about intentionality and design. Since humans evolved learning to scan patterns, we feel the need to search for something else in every cosmic object. This is a human obsession. We feel compelled to do it. When we see a sequence of events that appears purposeful, we instinctively assume the presence of intent. Preliminary compositional analysis does not show significant deviations from expected cometary chemistry. Difficulties in detecting specific gas types, water vapor, carbon monoxide, carbon dioxide, cyanide, reflect the challenge of observing faint emission lines against the distant background sky, not necessarily an unusual chemical composition. The experience with 2I Barissas here teaches patience. Most of that object's most interesting chemical features became evident only as it approached perihelion, and heating effects made gas production easier to detect. As 3I Atlas moves closer to the Sun and solar heating intensifies, its compositional fingerprints may yet become apparent. Morphological details revealed by Hubble imaging, slightly asymmetric dust distribution, offset between the core center and peak brightness, find ready explanations in the complex physics of cometary outgassing. Real cometary nuclei are not perfect spheres with uniform composition. They are irregular, with varying volatile concentrations and localized jets, forming asymmetric activity patterns from complex interior structures of ice and rock debris. Perhaps the strongest natural explanation for the apparent oddities of 3I Atlas lies in statistical reasoning. As our detection capabilities improve and we begin observing a larger number of interstellar comets, we should expect to find some with features that appear unusual or special purely due to random variation. For now, the fact that there are only 3 such interstellar objects generates substantial questions in our minds because we still lack sufficient data.
The Vera Rubin Observatory is expected to discover potentially dozens of interstellar objects in the coming decade. Basic statistics guarantee that some of these will, purely by chance, exhibit orbital geometries, brightness patterns, or other features that appear particularly striking on their own. This does not mean that unusual objects are necessarily ordinary. It means we must exercise extreme caution in distinguishing false patterns and misleading impressions of design from genuinely rare phenomena. The accumulated evidence supports a simple interpretation. 3I Atlas behaves largely as an interstellar comet, following the predictions of natural physics. Its unusual features reflect the inevitable variations that arise when examining objects from environments we do not fully understand. Viewed within the limits of our current observational capabilities, the cometary playbook, refined over centuries by studying objects within our own solar system, appears to work just as well for visitors from other stars. In other words, the rules humanity has learned in the Andromeda Galaxy apply without restriction to other galaxies as well. The cometary playbook can show similarities across galaxies. Magnificent, isn't it? This important discovery of the 2025 comet year once again demonstrates the power of natural explanations. Sometimes the phenomena that seem most extraordinary are the result of the most fundamental physical processes. The story of 3I Atlas reminds us that the secrets of the universe are mostly hidden not in complex theories, but in the simple and elegant laws of nature.
Like a pianist performing a complex Bach fugue, 3I Atlas dances through our solar system so perfectly that it becomes inevitable to wonder whether this dance is coincidental or prearranged. Clearly, for something to be prearranged, 4 elements are required: power, knowledge, will, and life matter. Not all of these elements are present, which leads us to a single creator. The topic is getting off track. Let's return to the main point. At this very point, one of the most debated topics in the scientific community comes into play. Is this interstellar object truly a natural comet, or is it a sophisticated alien probe from a distant civilization? The roots of this debate began with Oumuamua, discovered in 2017. Since that night, have you ever wondered whether as a civilization we are truly alone, or whether other civilizations exist? Avi Loeb, the famous astrophysicist from Harvard University, observed Oumuamua's unusual behavior and suggested that it could potentially be an artificial object, splitting the scientific community in two. Now the same debate reignites with 3I Atlas, and this time it becomes even more complex. When 3I Atlas's trajectory is analyzed, it follows a statistically astonishingly improbable path. Dear viewers, do you believe that millions to 1 probabilities happen by chance? Your answer is probably no. This event is a miracle. Almost everything around us is a miracle, from fruits and vegetables growing from black soil to the nitrogen balance in the air we breathe. Aren't these all miracles? The object moves in near-perfect alignment with the ecliptic plane, retrograde at exactly 175 degrees inclination. This is as if it somehow knows in advance the plane in which all the planets of our solar system lie. The sequence of planetary encounters detected by the Atlas telescope systems provides one of the strongest supports for controversial hypotheses. Passing Mars at 0.19 AU, Venus at 0.65 AU, Earth at 1.8 AU, and Jupiter at 0.36 AU, it appears like a meticulously planned grand tour. The probability of these being coincidences is almost zero, and for such an entity to exist before humanity, the 4 attributes required for its creation would be power, knowledge, life, and will. Hubble telescope observations revealed unusual patterns in the brightness distribution of the 2025 comet. Unlike traditional comets, most of 3I Atlas's brightness is concentrated on the sun-facing side, while the conventional tail remains very weak. Although this can be explained by forward scattering effects, some researchers suggest that it could indicate potential artificial illumination systems. Uncertainties in spectroscopic analyses also fueled the debate. The clear signals of standard volatile compounds expected in natural comets, such as water vapor and carbon monoxide, have not yet been detected. This might indicate that the object either has a very different chemical composition or gains its brightness through entirely different physical processes. Avi Loeb, the astrophysics professor at Harvard University, makes bold statements about 3I Atlas just as he did with Oumuamua. Avi Loeb, do you think he does this because he is brave or because he is extremely curious? You can share your answers in the comments. According to Loeb, if an advanced civilization wanted to study our solar system, it would behave exactly like 3I Atlas, appearing as ordinary debris, unnoticeable enough to avoid attention, yet sufficiently unusual to attract the interest of the scientific community.
Loeb's arguments are not mere speculation, they are grounded in solid physical principles.
The light sail hypothesis he developed to explain Oumuamua's non-gravitational acceleration can also be adapted and applied to 3I Atlas. However, this time the object exhibits clear cometary activity, which reinforces the camouflage theory. Loeb's research within the Galileo project aims to go beyond traditional observation methods. By using specially designed telescopes and AI algorithms, he attempts to detect subtle differences between natural bodies and artificial objects. This systematic approach also helps develop important protocols for how we might respond when encountering similar objects in the future. If an advanced civilization planned to study us without contacting us, what strategy would it adopt? If other civilizations exist beyond humanity, how do they manage to conceal themselves from us? Have they discovered invisibility, or do they camouflage themselves? The answer to this question forms one of the strongest aspects of the alien probe hypothesis, the camouflage theory. 3I Atlas exhibits perfect camouflage while appearing as a natural interstellar object. Coma formation, dust production, and increasing brightness as it approaches the sun, all of these conform to natural cometary behavior. Yet the subtleties hidden in the details suggest that this camouflage might even be intentional. The timing of the solar conjunction is particularly striking. During its closest approach to the sun, the object will disappear behind the sun from Earth's perspective, making detailed observations nearly impossible at its most active period. Could such precise timing be related to another civilization? Are they using Atlas 31 to observe us? Or is it simply the perfect design of the universe? For an advanced civilization, it would be possible to design a probe that looks natural. Artificial materials could mimic natural ice and rocks, controlled sublimation could produce realistic coma formation, and programmed activity periods could simulate the typical behavior patterns of natural comets. The artificial origin hypothesis has sparked major debate within the scientific community. Could 3I Atlas really just be a robot sent by another civilization to monitor us? On the other hand, conservative scientists, following the principle extraordinary claims require extraordinary evidence, remain skeptical. Carl Sagan's famous saying is often cited in discussions about 3I Atlas and forms the main argument of researchers who approach claims of artificial origin with caution. On the other hand, there are bolder researchers who argue that we must keep all possibilities open. This group reminds us that scientific conservatism can sometimes hinder revolutionary discoveries, noting that many major scientific advances in history, from Galileo to Darwin, initially faced fierce resistance. Official statements from NASA and ESA are quite cautious. Both agencies emphasize that 3I Atlas poses no threat to Earth, while avoiding taking a clear stance on artificial origin. This cautious approach aims both to maintain scientific credibility and to prevent unnecessary public panic. However, this official caution does not hide the intensity of debates among researchers. The peer review process examines papers on this topic much more carefully and demands much stronger evidence to support extraordinary claims. While this increases scientific quality, it also makes publishing innovative hypotheses more difficult.
Discussions about 3I Atlas have generated significant attention in the media and on social media. From every angle, a different voice emerged. If people trust someone else's hypothesis before real results are available, they may be immersed in misinformation. News articles titled, "Could it be an alien probe?" went viral quickly, but this both positively and negatively affected the quality of scientific discussion. The mainstream media's approach is generally geared toward sensationalism, clickbait headlines, the tendency to present scientific uncertainties as definitive conclusions, and the oversimplification of complex astrophysical concepts create misleading impressions among the public. On the other hand, this intense media interest has led to more resources being allocated to the topic and more detailed observations being conducted. On social media platforms, thousands of posts are shared under hashtags like 3I Atlas, Alien Probe, and Interstellar Object, while amateur astronomers have also started developing their own theories. This democratic approach to science can sometimes yield valuable observations, but it also increases the risk of conspiracy theories and misinformation spreading rapidly. Videos on YouTube with millions of views, viral short explanations on TikTok, and ongoing detailed discussions on Reddit show that the 2025 comet has become not only a scientific but also a cultural phenomenon. The Search for Extraterrestrial Intelligence Institute is one of the organizations closely monitoring 3I Atlas. Wouldn't you want to know if 3I Atlas is transmitting information to other civilizations? However, even if it is, it must be doing so while behind the sun, which means we cannot catch 3I Atlas in the act. SETI's radio telescopes check whether the object is emitting any artificial signals, but so far no meaningful signal has been detected. As part of the Breakthrough Listen project, some of the world's most sensitive radio telescopes, such as the Green Bank Radio Telescope and Parkes Telescope, are monitoring 3I Atlas. This systematic approach ensures analyses are based on scientific methodology rather than random speculation. In addition, optical SETI programs have also been activated. Artificial light signals such as laser pulses are being searched for because an advanced civilization might prefer to communicate this way. Hubble telescope data is also being reanalyzed from this perspective. The technological level we have reached in 2025 is a factor that makes these kinds of discussions possible, but also limiting. This situation will change in another 15 years. But which topics will the scientific world be able to solve more easily in 15 years? Such mysteries require the passage of years to be fully understood, but this does not mean that we cannot approach them with a low probability right now. Thanks to the detailed images provided by the Hubble telescope, we can understand the morphology of 3I Atlas, but we are still insufficient in spectroscopic analyses. The infrared capabilities of the James Webb Space Telescope allow for a more detailed analysis of the object's thermal properties. Natural comets and potential artificial objects may exhibit different thermal signatures. In particular, the detection of internal heat sources could provide critical evidence that strengthens the artificial origin hypothesis. The activation of the Vera Rubin Observatory at the end of 2025 will dramatically increase the detection rate of interstellar objects. If dozens of similar objects are discovered annually, it will become clear whether 3I Atlas is truly unusual or simply within the normal variation range. The development of artificial intelligence algorithms has the potential to revolutionize this field. Machine learning systems can analyze thousands of interstellar object datasets, detecting patterns and anomalies that the human eye might miss. Deep learning models can learn the subtle differences between natural and artificial objects.
Neural networks can analyze morphological details in Hubble telescope images to search for artificial patterns that may be hidden in the comma structure. AI systems specifically designed for spectroscopic data can detect chemical signatures that cannot be identified with traditional methods. If 3I Atlas is truly an artificial object, this discovery will be one of the greatest turning points in human history. It will influence many aspects of human thought, drive humanity toward further exploration, and most importantly, scientists will begin to investigate why the spy robot observing humanity is doing so and whether the civilizations monitoring us have hostile or friendly intentions. This situation will raise not only scientific, but also profound ethical and philosophical questions. Protocols prepared for contact scenarios generally focus on radio signals, while comprehensive plans for physical artifacts are lacking. The International Astronomical Union and the United Nations Office for Outer Space Affairs are working on developing new guidelines in this regard. These discussions are very valuable for science, even amid uncertainty. If an uncertainty is highly valuable for humanity, it means there is much we can learn from it. Don't you think this uncertainty can teach people a lot? It allows us to improve our methodologies, advance our technologies, and think more deeply about our place in the universe. When the news of the discovery of the interstellar object 3I Atlas spread worldwide in July 2025, the media reaction was almost as fascinating as the object itself. This mysterious visitor, detected by the Atlas telescope, found itself at the center of a global media storm within hours. How would you have felt in that media storm? I would have loved to see your facial expressions when you first heard the news. CNN aired segments discussing the possibility of an alien probe, while The Guardian published detailed explanatory articles on interstellar objects. Science journalists worked overtime to translate orbital mechanics into language understandable by the general public. Social media platforms, meanwhile, were in total chaos. Debates swinging between alien theories and serious scientific analysis turned that day's news into a figurative battlefield for the scientific world, with voices coming from every direction and the environment overflowing with storms of thought. When images from the Hubble telescope were released, public interest increased even further. These images, showing a bright coma and a weak tail, provided strong evidence that the object was a natural comet. However, the general public could not fully grasp the uncertain nature of the scientific data, and they were seeking definite answers. The public was, in a sense, waging an all-out battle against uncertainty with the scientific community, ready to do whatever it took to learn the truth and break down the wall of ambiguity. Official statements from NASA and the European Space Agency struck a perfect balance between scientific excitement and appropriate caution. Both agencies emphasized that the 2025 comet posed no threat to Earth, while also highlighting the importance of the scientific opportunity. This measured approach helped calm the public while keeping scientific curiosity alive. However, behind the institutional messaging, much more lively discussions were taking place among scientists. Avi Loeb and his colleagues argued for keeping the possibility of an artificial origin on the table, while the majority preferred natural explanations. This academic tension reflected both healthy scientific debate and philosophical differences regarding how potential discoveries should be handled. The discovery of 3I Atlas demonstrated humanity's maturity in international scientific collaboration. Hours after the announcement, observatories across 6 continents coordinated their telescopes toward the object. Professional and amateur astronomers shared data through the Minor Planet Center, creating a global research network. This network provided access to information to everyone, regardless of professional status, and at the same time enhanced human unity, increasing research efficiency by nearly a quarter. This coordination showed that we could rise above political tensions and competing national interests. Humanity's capacity to unite in the face of astronomical phenomena seems strong, even in times when cooperation on terrestrial matters was difficult. Could this have been an important signal for potential alien observers? What would happen if 3I Atlas transmitted this data to a mysterious civilization? Would it increase 3I Atlas's secrecy? Perhaps this is why we still have not obtained definitive evidence. Discussions about the interstellar comet on platforms like Twitter, Facebook, and Reddit offered a fascinating glimpse into human psychology. Hashtags trended within hours, memes proliferated, and conspiracy theories intertwined with plausible scientific explanations. Algorithmic influence exposed users primarily to content supporting their own beliefs, while opposing views were pushed into the shadows. This effect of digital echo chambers demonstrated how scientific facts could be distorted or exaggerated. Supporters of the alien probe theory gathered within their own groups, while skeptics created separate discussion spaces. Voices attempting to bridge the gap and provide balanced perspectives were relatively few and far between. Communication gaps between scientists and journalists resurfaced in the case of 3I Atlas. While scientific papers are inherently filled with uncertainties, the media usually seeks definite headlines and clear conclusions. This mismatch can lead to public confusion and misunderstandings. How many times did you get confused while reading these reports? This communication gap caused significant confusion, especially when new cases emerged. In particular, dramatic changes in size estimates from 20 kilometers in initial reports to just a few kilometers in later analyses provided important lessons on how the media handles scientific uncertainties. Some press outlets struggled to explain the transition from headlines like "giant alien ship" to conclusions such as "modest comet." Reactions to 3I Atlas also revealed different cultural attitudes toward extraterrestrial life and science. While the discovery was generally met with excitement and curiosity in Western media, some societies approached it with more caution, even concern. These differences showed that humanity is not yet united in its cosmic citizenship journey. The prevalence of alien contact in popular culture was another key factor shaping public reactions. Hollywood films, science fiction novels, and TV series influenced how people perceived the possibility of an alien probe. These works, often dramatic and frequently threatening, could create a gap between expectations and reality when faced with real scientific discoveries. The discovery of 3I Atlas also provided important lessons on how information spreads in the digital age. The speed at which the news circulated surpassed traditional media cycles, while simultaneously enabling misinformation to spread quickly. Social media algorithms favoring sensational content allowed conspiracy theories to reach broader audiences more easily than balanced scientific analyses. In such an environment of information overload, how can one find accurate information? Do you trust the news you see in the media, and do you verify the information you encounter? This situation underscored, once again, how critical scientific literacy is. The public's ability to understand the peer review process, statistical analyses, and scientific uncertainties focuses not just on accessing correct information, but on interpreting it correctly.
The human brain's evolutionary tendency to seek patterns in uncertainty was also evident in discussions about 3I Atlas. Even in seemingly random events, our minds, programmed to search for purpose and design, were inclined to notice regularities in the object's orbital characteristics that resembled human planning. This psychological tendency is both the driving force of scientific progress and a source of error. As with the case of Oumuamua, our inclination to develop exotic hypotheses to explain anomalous features can sometimes cause us to overlook natural explanations. Yet the same curiosity and skepticism also serve as the engine for real discoveries. Humanity's reaction to the 2025 comet also provided clues about our species' level of cosmic maturity. Our capacity to study a phenomenon methodically, without panicking, and through international cooperation could be a positive signal for potential alien observers. What if the things we discovered were actually aliens? How would humanity react? And how would the aliens themselves respond to us? Responses to the discovery of 3I Atlas revealed noticeable generational differences. Generation Z made the topic go viral by instantly creating memes on social media, while older generations preferred to obtain information through traditional media channels. This contrast offers insights into how future alien discoveries might be perceived and disseminated. Technological literacy was another important factor shaping reactions. Individuals able to interpret Hubble telescope data were less swayed by sensational media headlines, whereas groups lacking technical knowledge became more susceptible to conspiracy theories. To avoid getting lost in the sea of online misinformation, your technological literacy needs to be at a reasonably high level. Otherwise, you could also be swept into the information clutter. As a viewer, how would you assess your own technological literacy? Is it strong or weak? The economic implications of the interstellar object discovery cannot be ignored. A huge market emerged for scientific publications, conferences, and documentaries. Toy companies released 3I Atlas models, while the tourism sector began organizing alien hunting tours. This commercial interest demonstrated how scientific discoveries can be popularized. The technology sector also seized the opportunity. Telescope manufacturers faced increased demand. Space tourism companies offered interstellar comet observation packages, and even the cryptocurrency market saw derivative products like Atlas coin emerge, proving how widespread the economic impact of scientific discoveries can be.
The discovery highlighted gaps in our education systems regarding space science. Most students knew nothing about Oumuamua and struggled to understand what interstellar objects are. This revealed how slowly curricula adapt to rapidly changing scientific discoveries. At the same time, it created an enormous teaching opportunity. After the Atlas telescope discovery, planetariums and science museums recorded record attendance. Children's interest in space increased, and university astronomy programs saw a rise in applications. Have your children ever asked you questions about space? Did they ask about this discovery? Humanity's interest in space continues to grow every day. There were also more political implications than expected. Some world leaders announced that they considered alien probe theories as serious security issues. The Pentagon's heightened sensitivity after UFO reports illustrated how ambiguous objects like 3I Atlas could enter the security agenda. International space treaties also came under discussion. If the object were truly artificial, questions arose about which country would have what authority and how reception protocols would be implemented. These discussions revealed how unprepared humanity is for potential alien contact. The discovery of 3I Atlas also sparked various reactions among religious communities. Some groups interpreted it as evidence of the grandeur of creation, while others debated the theological implications of the possibility of alien life. These discussions showed how science and belief systems interact when faced with major discoveries. How did these discoveries affect you religiously and philosophically? Do you think the impact was positive or negative? Did they change your beliefs? Philosophers examined the epistemological questions raised by the 2025 comet. Topics such as how we perceive reality, how we cope with uncertainty, and the distinction between scientific truth and media truth were intensely debated in academic circles. The reactions and discussions we observed in this first section served as a mirror showing where humanity stands, independent of 3I Atlas's physical characteristics. The discovery became not only an astronomical event, but also a sociological phenomenon, reflecting the complexity and diversity of our society. The discovery of 3I Atlas did not only spark a technical debate within the astronomy community, it also raised deep philosophical questions about scientific methodology and epistemology. The tension between Avi Loeb's open-minded approach and traditional scientific conservatism divided scientists into two camps. Loeb, leading the Galileo project at Harvard, argued that keeping the alien probe hypothesis on the table was not just a scientific necessity, but also a matter of intellectual honesty. He suggested that hiding behind the phrase, "extraordinary claims require extraordinary evidence," carried the risk of missing potentially revolutionary discoveries. So, what is the measure of open-mindedness in science? Should we embrace every idea or believe every unproven hypothesis? How open should we be to ideas in science? On the other hand, scientists in the opposing view argued that supporting exotic explanations with insufficient evidence would undermine scientific credibility and feed conspiracy theories in the public. They pointed out that Hubble telescope data clearly showed cometary activity and that natural explanations were entirely sufficient. Discussions on the orbit of Atlas and timing of Atlas gave rise to an entirely new hypothesis, the humanity test theory. According to this theory, the interstellar object's primary purpose might not be to study our solar system, but to study us. An advanced civilization could be interested in learning how technological species react when confronted with potential contact.
From this perspective, 3I Atlas's ambiguous characteristics create a perfect experimental design. If it were too obviously artificial, it could cause panic. If too obviously natural, it would attract no attention. Instead, it presents a puzzle in the middle, convincing enough to seem natural, mysterious enough to be potentially artificial, perfect for testing humans. But why would a mysterious advanced civilization want to measure humanity's response to another civilization? Are we being treated as test subjects? Proponents of the theory note that the global reaction following the discovery, including international cooperation, media dynamics, and institutional coordination, provided potential observers with comprehensive information about humanity. Everything from how we make decisions, how we deal with uncertainty, to our technological capabilities and social organization skills was on display. During the 2025 Comet discussions, the concept of cosmic citizenship gained prominence both in scientific circles and popular culture. This concept reflects humanity's efforts to redefine our place in the universe. We may now need to see ourselves not only as Earth citizens, but potentially as members of a broader galactic community. The SETI, or Search for Extraterrestrial Intelligence community, emphasized that the discovery of the interstellar comet had symbolic significance for this transition. For the first time, we could systematically study a physical object from another star system. This experience provided valuable practice in how we might behave in real alien contact, and it also gave insight into humanity's responses. This means that if an alien attack were to occur, humanity could control its emotions more effectively. Cosmic citizenship is not just a scientific concept, it is also a framework with ethical and political dimensions. If we are truly not alone in the universe, questions about how we interact with other intelligent species, which values we share, and which protocols we follow become increasingly important. With the imminent activation of the Vera Rubin Observatory, discoveries like 3I Atlas are expected to become routine. Predictions suggest that 6 to 50 interstellar objects could be detected annually, forcing society to reconsider how it responds to such discoveries. This increasing rate of discoveries carries the risk of media fatigue. The first few discoveries may attract significant attention, but once they become routine, public interest may wane, potentially causing important findings to be overlooked. Science communication experts will need to develop strategies that emphasize the unique significance of each discovery. At the same time, more sophisticated analysis tools and protocols are necessary. The success of the Atlas telescope system shows that automated detection systems can be highly effective. However, the post-detection characterization process remains largely manual and time-consuming. I will ask this question to technology enthusiasts. How much can artificial intelligence accelerate this process? In your opinion, is it very effective or limited? AI can generally speed things up, but only if it can detect the target. If it cannot recognize what it is supposed to analyze, it cannot perform the task. The 3I Atlas experience demonstrated that alien contact protocols are necessary not only for radio signals, but also for physical objects. Currently, there are no standardized procedures for dealing with ambiguous objects. Who decides, which tests are performed, how is information shared, and who informs the public and when?
The United Nations Office for Outer Space Affairs, UNOOSA, has announced that it is forming working groups on these issues. However, legal frameworks, international coordination mechanisms, and emergency protocols are still under development. The 2025 Comet case highlighted how critical these gaps can be. In particular, potential threat assessment is complex. 3I Atlas poses no physical threat, but we may encounter objects that pass much closer to Earth in the future. How will we react if a naturally or artificially ambiguous object approaches very near? Could 3I Atlas, under the command of a mysterious civilization, follow a hostile path against humanity? Could it contain cosmic weapons, or will it act peacefully? These are questions that only time will answer.
The discovery of 3I Atlas tested how prepared our current scientific institutions are to handle such extraordinary findings. Overall, the outcome was positive. Rapid coordination, effective data sharing, and a measured public relations approach were demonstrated. However, some shortcomings also became apparent. The peer review process is too slow to keep up with rapidly unfolding events. There is a lack of trust between the media and scientists. The public is insufficiently equipped to understand scientific uncertainties. Based on this experience, some institutions have begun developing emergency protocols. The Hubble telescope and other major observatories have established rapid observation programs for extraordinary discoveries. Scientific associations are working on more effective communication strategies with the media. Humanity's response to the alien probe hypothesis revealed how quickly our species can show cultural adaptation. Within a few months, discussions about interstellar objects became mainstream. Topics that were previously debated only by science fiction enthusiasts began appearing in dinner table conversations. This cultural shift indicates how ready humanity is from a cosmic perspective. We did not panic, we did not go mad, we did not cause civilization to collapse. Instead, we approached the situation with curiosity, caution, and an open mind, actually showing good results. Has humanity entered the cultural adaptation process faster than we thought? Perhaps we had begun maturing as a species earlier than expected. Of course, this is only a test case. Real alien contact could trigger far more dramatic reactions. Nevertheless, the 3I Atlas experience shows that, at least, the scientific community and media systems function reasonably well. The discovery of 3I Atlas reshaped our existential questions. As the likelihood that we are the only intelligent species in the universe decreases, the way we define ourselves changes. This shift is both humbling and exciting. Some philosophers argue that the mere existence of interstellar objects is powerful enough to shake our anthropocentric worldview. Physical evidence from other star systems makes the vastness and diversity of the universe tangible. Are we truly a dominant, magnificent civilization at the center of the universe? Or are we a species perfectly suited to being a relatively weak observer at the edge of the cosmos? Starting with Oumuamua and extending through 3I Atlas, the experiences we have lived through are enhancing humanity's level of cosmic awareness. We no longer see ourselves solely as a species residing on our planet. We are beginning to view ourselves as cosmic beings capable of potentially interacting with our galactic neighbors. This shift in consciousness will, over the long term, influence everything from our science policies to artistic production, from education systems to social values. The 2025 comet may go down in history as the symbolic starting point of this transformation. Science is fundamentally a dialogue between two things, the things we think we know and what the universe actually shows us when we look closely enough. For 3I Atlas, this dialogue has been enlightening, frustrating, and sometimes contradictory. The discussions in these dialogues have dragged humanity to the very bottom of the curiosity pit. Nevertheless, humanity's curiosity has not diminished. On the contrary, it has increased even more. It is a perfect example of how the most interesting discoveries emerge from the gaps between certainty and ignorance. First, let's start with what we can say with confidence. Astrometric data, the precise measurements of the object's position over time, provide strong evidence for 3I Atlas's interstellar origin and hyperbolic orbit. These evidences can affect humanity both negatively and positively. They could be the first steps toward a civilization that might threaten humanity, or the first steps toward another civilization that could help humanity. Multiple observatories worldwide have tracked this object for months, creating an observational network that determined its orbital characteristics with high precision. The approximate eccentricity of 6.1, the inclination of 175 degrees, and the sequence of planetary encounters are calculated as accurately as celestial mechanics allow. These numbers are based on calculations continuously refined since the initial discovery by the Atlas telescope.
The probability of this information being wrong or coincidental is very low. The probability of an entity watching us is much higher. What if a civilization is truly observing humanity? Why are they observing humanity? What are their purposes? These questions may remain gathering dust behind the curtains of secrecy for a long time. Hubble Space Telescope observations form another pillar of reliable data. These images clearly show a developed coma, evidence of dust emission in the sunward direction, and a faint anti-solar tail. These are the distinctive features of an active comet. Surface brightness modeling constrains the nucleus size to a radius smaller than 2.8 kilometers, possibly even smaller. Dust production rates, measured between 10 to 120 kilograms per second, fall within reasonable ranges for cometary activity several astronomical units from the Sun. Photometric measurements from multiple facilities provide consistent evidence that the object gradually brightens as it approaches the Sun, showing patterns similar to other comets at comparable distances. These actions provide evidence that the 2025 comet is approaching its peak point as days progress. These solid islands of information are surrounded by oceans of uncertainty that reveal how much we do not know about 3I Atlas and interstellar objects in general. Presenting decisive, bold hypotheses into such an uncertain void means offering hypotheses that are more decisive and bolder than experts like Avi Loeb, and this void forces scientists to do so. Spectroscopic data, however, remain tantalizingly incomplete. Despite specialized observation campaigns conducted at multiple facilities, attempts to detect specific gas species, water vapor, carbon monoxide, carbon dioxide, cyanide, have provided only upper limits rather than clear detection results. This does not indicate unusual chemistry. Faint emission lines are extremely difficult to detect against background sky noise, especially for distant objects with modest activity levels. The I. Borisov experience here provides both hope and caution. It should be remembered that only when that object approached the Sun and heating effects elevated gas production to more easily detectable levels did its most distinctive spectroscopic features become visible. 3I Atlas may also reveal its chemical fingerprints as solar radiation intensifies, but we will not know until observations are completed and analyzed. The findings we uncover may provide evidence that humanity is being observed by other civilizations, and, perhaps even better, we might locate where 3I Atlas has sent a signal. Just imagine what technologies might other civilizations possess. Detailed morphological analysis remains limited by the fundamental challenges of separating nucleus properties from coma contamination. Although Hubble's sharp vision can separate these components better than ground-based telescopes, modeling still requires assumptions about dust particle properties, size distributions, and scattering efficiencies. These assumptions add systematic uncertainties to all derived parameters.
The broader context of interstellar object research adds another layer of complexity to interpreting 3I Atlas. With only 3 confirmed detections, Oumuamua, 2I Borisov, and now 3I Atlas, we lack the statistical baseline necessary to distinguish normal variation from genuinely anomalous behavior. This limitation makes humanity's task considerably more difficult, and it also complicates processing data from the Hubble telescopes. As if that were not enough, Hubble's data collection operations also take weeks. What appears unusual for 3I Atlas may prove to be completely typical once we observe dozens of similar objects. This situation increases the significance of the Atlas telescope system's discoveries. Each new detection provides valuable data points that deepen our understanding. The Vera Rubin Observatory promises to transform the situation dramatically. With its 8.4-meter primary mirror and 3.2 gigapixel camera, Rubin will scan the entire visible sky every few nights starting from the mid-2020s. Conservative estimates suggest that, depending on size distributions and the efficiency of follow-up observations, it could detect 6 to 50 interstellar objects per year. These numbers are only starting figures for 2025. The 2025 comet is just beginning to heat up. In the future, we will have abundant data before long, but how useful the data will be is crucial, so much of it could be unhelpful information.
This flood of new discoveries will provide the statistical power needed to address many of the existing questions about interstellar objects. Are ecliptic alignments truly rare or a consequence of predictable selection effects? Do unusual brightness patterns represent exotic physics or natural variations in dust properties? How common are objects with the specific combination of characteristics seen in 3I Atlas? The Rubin era will also bring new challenges. The rapid discovery rate will strain our ability to conduct detailed follow-up observations of every interesting object. This limitation could cause us to miss discoveries that would be treasures for us. Missing discoveries serves as a cautionary warning for humanity to be more careful. Automated classification systems will become necessary to manage the data flow. However, these systems must be trained on the limited sample of objects we have worked with so far. Early decisions about which discoveries deserve intensive study could bias our understanding of the broader population. International coordination will become even more critical as discovery rates increase. Current manual follow-up observations and careful individual analysis systems cannot process dozens of new objects per year. We will need more efficient protocols to share observing time, coordinate spectroscopic campaigns, and disseminate results quickly enough for time-sensitive observations. The current success of the Atlas telescope system provides a promising foundation for future challenges, but the time period that will truly test the Atlas telescope is the Rubin Revolution. The Rubin Revolution will put the Atlas telescope through a demanding trial.
The 3I Atlas experience has highlighted both the strengths and the limits of our current approach to studying unusual astronomical phenomena. Under intense public interest, we demonstrated extraordinary ability to coordinate rapid multi-facility observations and produce sophisticated analyses. At the same time, it revealed significant gaps in our capabilities and understanding that will need to be addressed as such discoveries become more common. Perhaps most importantly, the 3I Atlas observations provided critical practice in managing uncertainty and conveying scientific nuance during potentially revolutionary discoveries. These practices will allow us to maintain control if another civilization is found, and will be vital in such situations. The skills we developed in distinguishing true anomalies from observational artifacts and reasonable speculation from unfounded claims will become necessary when encountering objects whose interpretation is even more challenging. The current limits of our knowledge about 3I Atlas reflect the natural difficulties of working with small, distant, fast-moving objects using limited observational resources. At the same time, they also reveal the extraordinary progress we have made in developing the theoretical frameworks, instrumental capabilities, and analytical techniques necessary to extract meaningful science from limited data. Bold hypotheses by researchers like Avi Loeb emphasize the balance between scientific conservatism and openness to extraordinary discoveries. Although Avi Loeb's approach unsettles some astronomers, it raises some important questions. These questions are, what will we do when we find a mysterious civilization? And what will we gain? The argument, starting from Oumuamua, to keep the possibility of artificial origins of interstellar objects on the table has crystallized methodological differences within the scientific community. This debate has revealed deep philosophical differences, not just about public UFO theories, but about the nature of the scientific process itself. Critics argue that entertaining alien probe hypotheses without compelling evidence undermines scientific credibility and fuels public conspiracy theories. Advocates counter that excessive conservatism carries the risk of missing truly revolutionary discoveries, and that the potential consequences of contact with extraterrestrial intelligence justify more aggressive investigation of anomalous objects. These views will enable the 2025 comet data to be interpreted in a more understandable and improved manner. Our current observational infrastructure is primarily designed to study natural phenomena and may not be optimal for detecting subtle technological signatures. Artificial objects may emit infrared signatures different from natural bodies, exhibit structural features visible only at high resolution, or display orbital modifications too small to be detected with standard astrometric techniques. The Galileo project represents an initiative to address these issues through systematically designed search strategies, particularly in near-Earth space, to detect technological artifacts. The goal of such a project should be to exceed the limits of the Hubble telescopes, but for now, the project targets simple things, which means its potential has not yet been fully utilized. Rather than discussing interpretations after objects are discovered, the project aims to deploy instrumentation optimized to distinguish between natural and artificial phenomena. The concept of astroarchaeology expands this idea to systematic searches for technological artifacts throughout the solar system. Just as terrestrial archaeology studies ancient human civilizations through material remains, astroarchaeology will search for evidence of past visits by examining objects in unusual orbits with anomalous compositions or suspicious geometries. These videos are really made with great effort and go through many research processes. Therefore, your support is very valuable to me. Don't forget to like the video and subscribe. Thank you in advance. See you in the next video.